Welcome everyone. Shubho Bijaya to everyone. So this is our lecture after the small puja vacation that we had. So today's talk is a very interesting one. Today's talk is based on one of the foundations and one of the groundbreaking theories in all of physics, that is electrodynamics. And today's speaker is Debapriyo Chowdhury. Debapriyo did his bachelor's from St. Xavier's College, and now he is in IISc Bangalore. So without further ado, so let's give it to Debapriyo. So Debapriyo, you can go ahead and get started.
Okay. So good evening everyone. My name is Debapriyo Chowdhury. I'm an integrated PhD student at the Indian Institute of Science. And today my talk will be based is on the topic of essentials of quantum electrodynamics. So as you know, so quantum electrodynamics is basically the quantum to study the quantum nature of matter when it interacts with radiation. So it's a very vast topic. So since I'm getting 1 hour, I will focus on the essentials, and let's see how much we can do, and let's enjoy first. This topic is a very interesting topic, so I want all of us to have fun. So let's see let's see how much we can proceed. Okay. So quantum electrodynamics is basically divided into 3 major portions. So first is spinless particles. So basically, what are spinless particles? Spinless particles are particles which are whose quantum fields are scalar in nature. They are neither vector, neither they are spinors. I will explain what a spinor is to you, but they are simply the fields are simply functions of space and time with no other vector nature or a spinor nature. So this is a spinless. This represents a spinless particle. Second comes the Dirac field. The Dirac field is basically the quantization of the Dirac equation. Dirac equation is a classical equation whose quantization leads to the Dirac quantum field. And the Dirac quantum field, when quantized, gives rise to some objects called spinors. Again, this is another type of field, another type of quantum field which is a spin half. Okay, so this is basically a fermionic field, and most importantly, there are many other types of fermionic fields which are spins half of odd integers, but we will specifically focus on the spin half fields. And last thing, we will see how the Dirac fields and the spinless fields they interact with light. That is the quantum electrodynamic nature of spin half and spinless particles. So starting, I mean, this is a lot of mathematics, I know, but let's see what is happening here. So first of all, we are deriving the Feynman propagator of scalar field. What is a scalar field? The scalar field is a solution of the Klein-Gordon equation. Now, what is the Klein-Gordon equation? Klein-Gordon equation is basically the most simplest of the simplest of all the relativistic wave equations. It simply has a del square term and a mass square term, which acts on a field phi, which is a function of x and the space x and time t. And since this equation, okay, so the equation is basically del square plus m square phi equal to 0. So this equation has a simple solution in the form of of an exponential term, which is simply a Fourier exponential term, e to the power minus ipx and e to the power plus ipx. So most general solution can be written in this form. Okay, so now since we are talking about quantum fields, so phi must be promoted to an operator. So these AP and AP dagger are operators, and this 1/2 EP, this has been taken to make this a Lorentz invariant measure. Now, what is a Lorentz invariant measure? This I will not explain this to you because I will not have the time. Simply take this as an integration measure, Okay, so now since we have the field phi, we try to calculate now we define a propagator. What is a propagator? Propagator is basically the vacuum expectation value, of two fields. Okay, so one is placed at phi x, one field is placed at x, the other is placed at y. So when we take the vacuum expectation value of these two fields, we get, when we calculate this, we get something like this. I mean, see, there are two operators. Okay, so one is P, the other is, so one is AP and the other is AP dagger. So if we take the product of phi x and phi y, okay, and we take two integration variables P and P prime for x and y, then only AP and AP prime dagger will contribute to this inner product. The other inner products will simply give 0. Okay, since this will raise this to a, so this is a raising operator. So if this is a raising operator, this will simply raise this 0 to a momentum level P prime, and this will again raise this bra to a momentum level P, and only this will give a non-zero term. Other all terms will cancel out. Other all terms will give 0 inner product. So if we calculate this inner product, we simply get this. Delta functions from here. Since we know inner products give us delta functions, and integrating over the delta functions will give us this. Over the P prime integral, if we do, we will get this. So this is called a propagator. Okay, now I define the final propagator as the time ordered product of the expectation values. I mean, I define the final propagator simply like this. It is the expectation value of the time ordered product of operators, of two operators. So it is equal to d of x minus y when the x naught is greater than y naught, or the time component of x is greater than the time component of y, or it is dy minus x when the time component of y is greater than time component of x. Okay, so this is the definition of time ordered product. Okay, next. So how do I so I define the final propagator like this. Now I want to find an expression for the final propagator. So how do I do that? So I have okay. So I claim that if I represent the final propagator in this fashion, I will get back these values. So to prove my claim, I simply do a contour integral. Now to do a contour integral, so the final propagator is such that we have to choose a contour, or we can simply use the I epsilon prescription. The final propagator, to calculate the final propagator, we have to choose the contour in a specific fashion, and the fashion is like this. So we take here, we take this contour coming from negative infinity, and we take, you can see the contour. We take like this, and we go and we take above the plus EP, and then we go to plus infinity, and then we have to close the contour in some way. So in what we have to close, that will depend on the value of x minus y. Okay. So next. Okay. So see, we can, since this contour, this kernel has two poles, one at plus EP and the other at minus EP. If we do the P naught integration, this has 4 integrals. So if we do the P naught integration, we simply see that if x naught is greater than y naught, okay, if x naught is greater than y naught, then this term will be positive, right? Because this is basically x naught minus y naught times plus other space variables. So this is positive, and there is a lemma in complex variables that called Jordan's lemma, which gives that if this is positive and there is a minus sign here, then we close the contour in the lower half plane. Okay, so if we close the contour in the lower half plane, then and we take the residues, then we simply get this, right? Hope this is understandable. If it is not understandable, I will make you understand later. So I have to proceed now. So okay, so this is the residue of the contour integral. If we put the residue here, and while doing the dp naught integral, then we get something like this. So this 2 pi cancels out, okay, and this I minus 1, this minus 1 is there, so this becomes plus 1, so we get this. So my claim is justified. So I get back dx minus 1. Similarly, if y naught is greater than x naught, we close the contour in the upper half plane in the anti-clockwise direction, and we again if we do the calculation, we take the residues and we do the calculation, we get dy minus x. So my claim is justified. If so, we can really represent the Feynman propagator using this integral. Okay, now since we are specifying a particular path to make this propagator justified, we can do one more thing. We can take limit epsilon tending to infinite limit epsilon tending to 0, and we simply take this I epsilon prescription where the poles are shifted slightly below and slightly above in the fourth and the second quadrant, and we get the same result again. Okay, now we were looking at real scalar fields until now. We will look at complex scalar fields now. So what is a complex scalar field? A complex scalar field is nothing but simply two real scalar fields, phi 1 and phi 2, where psi equals to phi 1 plus I phi 2 and psi star is equals to phi 1 minus I phi 2. Okay. Now, if we take this Lagrangian, okay, so what is a Lagrangian? So Lagrangian is nothing but which gives us the equations of motion using the Lagrange equations. If we take this Lagrangian and we again we find out the equations of motion, we will get two equations. Both equations will be similar to the Klein-Gordon equation, only with psi and psi star. Two equations. The first has psi star, psi, and the second has psi star. Now again, this is a quantum field, so we raise this to an operator. So as we raise this to an operator, we get two fields. The most general expression is this. Now you might be wondering, there are two kinds of operators here. In the scalar field, there was only one kind of operator. Okay, but here we see there are two kinds of operators. Why so? Because if we do not take two kinds of operators, simply if we dagger psi, we will get psi back again. So to make this truly a complex field, we need two operators. Now these two operators are very huge significance. They represent the creation and annihilation operators of a particle and an antiparticle. These operators have these commutation relations, okay, and the other commutation relations among them. For example, all the creation operators commute among themselves. All the anti-commute among themselves, but only the creation operator and the annihilation operator don't commute. They keep these commutation relations. Okay, so I'm moving on now. Okay, so we are going to calculate our first quantum field theory amplitude. So what are we seeing here? So this is meson. So meson is a scalar particle. We are assuming a spin zero meson. A meson is decaying into a nucleon and an antinucleon. Okay, so the nucleon, again, the nucleon we are assuming spinless, and the antinucleon also we are assuming spinless. We will come to spin later. So a meson is decaying into a nucleon and an antinucleon. So the initial state is basically this. The initial state is basically, so 2EP root over 2EP is a normalization. It is a convention to make the delta function commutators consistent, mathematically consistent. So AP dagger operates on the vacuum and gives us the initial state, which is one meson, and the final state is basically a nucleon, which is given by BQ1 dagger and an antinucleon which is given by CQ1 dagger. Where is my pointer? One second. Ah, yes. So these act on the vacuum and give us the final state. Now we want to calculate the amplitude, right? So what is the amplitude? Is basically the inner product of the scattering matrix with the initial and the final state. The scattering matrix basically is the time evolution operator with the initial time of what is happening. The initial time taken at minus infinity, the final time taken at plus infinity. And this scattering matrix acts on the initial state to evolve it, and then we take its inner product with the final state. Now, you might see there is a G factor coming here. Now, this G is basically nothing but the coupling. It is basically the coupling factor of the interaction. When a meson interacts, decays into a nucleon and an antinucleon pair of momentum Q1 and Q2, that interaction coupling term has a strength which is given by G. Now we are looking at the lowest order, means of Feynman diagrams, only at the tree level. So this has only G, not G square or G cubed. Okay. So this phi, so what is my pointer? Okay. So this, okay. Now if we take a look at the interaction, you might see there is a psi dagger field, there is a psi field, and there is a phi field. The phi represents a meson, the psi represents a nucleon, and the psi dagger represents an antinucleon. Now, if we expand this I according to this formula, we get something like this, right? And the psi and psi dagger field are left undisturbed for now. Okay, so now again, so this AP dagger term and this root over 2 AP term, they give us the meson. Now this meson will decay. Okay, and one more thing. Okay, one second. One second. Okay, okay. And so phi, now phi is a scalar field, right? So phi has an expansion. It is given by AK and AK dagger. Now that AK dagger, if it acts on this 0, this will have no contribution with this inner product because there are psi and psi dagger fields here. Now if we take AK dagger, it will simply create another meson which has no relation with our given decay. So we have to annihilate the meson, right? So we have to take only the AK part and leave the AK dagger out. So we take the phi field, we take only the AK dagger part, only the annihilation part, and we simply expand the phi in such a way such that we take the AK part only. Now this d2k is simply the phi field expanded. Okay, this integral of the phi field. Now again, so okay, so this e to the power minus ikx. Okay, so AK and AP dagger, we have the commutation relations, right? If you remember, we have the commutation relations AK and with AP dagger gives us delta to 2 pi cube delta cube k minus p. So if we have the delta function, we can integrate over the k integral, and we simply get e to the power minus ipx here. The 2 pi cube will cancel out with the delta function, and we simply get e to the power minus ipx. So now we have to expand this psi dagger and psi operators and see what happens. Okay, so this will cancel out because p and k will simply cancel out because k and p will be equal due to the delta function. Okay. Okay, so now we expand the psi and phi fields. So this is the expansion, as we noted earlier. As we expand, okay, so there are many terms that will come. Again, so similarly, there are many terms that will come. Only this term will contribute to the amplitude once we expand. So K1 and K2 are the expansions of the psi and psi dagger fields. Okay, and this E root over 2E Q1 and Q2 are the outgoing momenta of the nucleons. This comes from the expansion of psi and psi dagger fields. Again, we do the delta function commutation relations. Using the delta function commutation relations, we do the K1 cube integral, we do the K2 cube integral. These integrals we do, and the delta functions all. Okay, so after we do the calculations, all delta functions will give rise to different integrals, and all these factors will cancel out, and at last we'll get only one delta. We will have remaining only one delta function. This delta function, that is Q1 plus Q2 minus P. Now, so we do the K1 integral, we do the K2 integral, and also we do the X integral using all the delta function and the commutation relations. Okay, so all the factors will cancel out, all the delta functions will cancel out. Only one delta function will remain, that is this delta function. So we can see that we are left with a minus Ig coupling term. Now this minus I comes from the Dyson formula of the lowest order, of the lowest leading order in the Feynman diagrams, and G is the coupling, 2 pi to the power 4 is the normalization, and this delta function ensures the momentum conservation at the vertex. Okay, so we will come to Feynman diagrams just later. So just for now, you can see that the momentum is conserved at the vertex. So we get our first quantum field theory amplitude. Okay, so we look at one more example, which is a nucleon-nucleon scattering. Here there are two psi fields, so there are two nucleons. They scatter into two nucleons. So initially there are two nucleons. Finally there are two nucleons. So initial state is given by this, as was previously given. There are two dagger operators, B dagger P1 and B dagger P2, which are the initial nucleons, and there are final B dagger P1 prime, B dagger P2 prime, which are the final nucleons. Okay, the initial nucleons are this, and the final nucleons are this. This is given by the state I and F. Again, so this is a Feynman diagram. Okay, so how to give this? So this as you can see, this is a coupling term to the power 2. So why there is a 2? Since psi and psi simply will converge to a vertex. So I will come to vertices in a few moments. Give me some time. So psi and psi will converge to a vertex. There will be a propagator, and then two psis will again emerge from the vertex. So there are two vertices. So since there are two vertices, we get a G square term. There is also a minus I. Again, the minus I comes from the Dyson formula. This 2 factorial is equal to 2. This also comes from the Dyson formula. Dyson formula is simply the exponential expansion of the interacting Hamiltonian. Time ordered exponential expansion. Okay, I will. If you have some questions, I will surely answer them. Okay. So again, if we expand this term using all the expansions of psi dagger x1, psi x1, phi x1, psi dagger x2, all these expansions, if we look at the expansion, we will see that only this term will contribute to the Feynman diagram. The other terms all will give 0 results. Okay. Now these colons are called normal ordering. Normal ordering is what is called all the annihilation operators are to the right and all the creation operators are to the left. Okay, and this is called a contraction. This is nothing but the Feynman propagator. What we learned there, this is nothing but the Feynman propagator. This simply propagates the field phi from x2 to x1, right? So this Feynman propagator will simply give an integral over that kernel that we calculated 1 by p I by p square minus m square plus I epsilon. The other terms we have to calculate using their expansions and the initial and final states. Okay, so once we calculate this, again, if we expand all of this and we calculate using all the normal ordering, and we take all the creation of operators on the right and all the creation operators to the left, all the annihilation operators to the right, and if we calculate inner products using various integrals and delta functions, we end up with these terms. Nothing else. All the delta functions will cancel out, all simply will cancel out, and we will get these terms remaining. Okay, so if we multiply these, we open the bracket and we get these terms. x1, x2 means simply replacing x1 and x2 in the previous. What we had, if we had x1 here, we will have x2 here. Okay, simply replacing x1 and x2. This means. Okay. So, okay, so this is this term. This is this term. So if we calculate, so this is the Feynman propagator of the phi x1 and phi x2 field. I hope you can remember that. And this d4x1 is coming from this integral, and the d4x2 is coming from the other integral. This I explained, and this is the bracketed term in the expansion. Now if we again do these d4x1 integrals and d4x2 integrals, we will have delta functions. These delta functions will have something, since there is p1 prime minus p1 here, and also there is x1 here, x2 here, there are also x1, x2 here. If we do the integrals, we will get delta functions like this, right? So there is a delta function here, there is a delta function here, there is a delta function here, there is a delta function here. Now this delta function will be such that they will be matching, means two delta functions will be similar, so they will cancel out the two here. Once they cancel out the two, we will get two terms like this. Again, we can do the k integral. If we do the k integral, then we'll get a single delta function term like this. Okay, and which we have taken common, and inside this k will be replaced by p1 prime minus p1, right? Since there is a k integral, so k will be replaced by p1 prime minus p1 or p1 minus p1 prime, and this k will be replaced by p1 minus p2 prime from here. We do this integral and we do this integral. The other delta functions we will take common outside. So we get the second quantum field theory amplitude. Remember, these are only scalar particles. We have not included spin until now. So this is the quantum field theory amplitude of two nucleons scattering into two nucleons. So we have done a bit of scalar quantum field theory. Now we will enter what is called the spinor quantum field theory, or the Dirac field. Dirac field has an action which is given by this. This action has a Lagrangian and a d4x term. This Lagrangian is psi bar x, I gamma mu del mu minus m psi. Now psi bar and psi are the two conjugate fields, Dirac conjugate fields of the which satisfy the Dirac equation. So what is the Dirac equation? We get the Dirac equation by varying, using the Euler-Lagrange equations. By varying this Lagrangian and using the Euler-Lagrange equations, we will get this Dirac equation. Now this gamma mu are the Dirac gamma matrices. I have not given the representations because those are not important. What are important is the properties of the gamma matrices. Okay, so gamma matrices are very important, and they are fundamental to whatever we do in quantum electrodynamics. There are many representations of the gamma matrices, but I am not going to do them. Okay, so we can derive two equations from here. Since these are two variables, psi bar x and psi x, if we vary with respect to psi, we get the conjugate equation. If we vary with respect to psi bar, we get the Dirac equation. This is the conjugate equation of the Dirac equation, and this is the original Dirac equation. Okay. Simply is given by this. This is a relativistic equation which is first order in both the time and space derivatives. If we square the Dirac equation, we simply get back the Klein-Bardeen equation. The Dirac equation has the free Dirac equation without any interaction terms present, has a simple, very simple ansatz. The ansatz is given by this, where e to the power minus IPX is simply the plane wave part, and UP is the spinor part. Now, what is UP? I will explain. So, gamma mu matrices, okay, they are basically 4-dimensional matrices. So, UP, we cannot have gamma mu matrices of dimensions lower than 4. They are at least of dimensions 4. So, UP is basically the spinor, a spinor of a 4 cross 1 spinor. Okay, it has 4 components. It satisfies this equation. Right? If we put this ansatz into psi, we get back this equation, right? Because del mu and is an operator, and whose eigenvector is p, right? So we get back this equation. If we expand this equation into this, so we have used the expansion of the gamma matrix here. So gamma matrix is okay. So we have used the expansion of the gamma matrices. Okay, so gamma, I have not given the representation. So okay, no problem. So gamma 0 is basically -1 and -1, right? And the gamma I -1, -1, 1, 1, where -1, -1, 1, 1 are simply the unit matrices of order 2, okay, of dimensions 2, and the gamma I matrices are simply the Pauli matrices. Okay, so Pauli matrices here with diagonal component 0, and the off diagonal components, the Pauli matrices. Okay, so I hope you can understand this. This sigma mu bar is basically 1 minus sigma I. This is a 4 vector again of the Pauli matrices, and sigma mu is 1 sigma I. So this sigma mu and sigma mu bar are present here. So this is basically the gamma matrix. We have expanded using the gamma matrices. Now this equation has a solution. The solution is of this form. I am not giving the proofs, because if I give the proofs, I will not be able to finish the talk. Okay, so this root over p dot sigma is basically, we are taking the positive square root of the eigenvalues of these matrices, and the xi's are simply 2 component spinors. They are 2 component convectors. Okay. Next. This Dirac equation also has a property that it satisfies also a solution with negative frequency. That is, if we put e to the power plus IPX, it also satisfies the same equation. Again, if we do the calculations, we will get again this VP. Now, similar to this VP, we can get, if we substitute this VP into the Dirac equation, we get a solution like this. Now, eta and these eta are also again 2 component spinors. Obviously, this is nothing but the the positive square root of the eigenvalues of the sigma matrices dotted with p. These are all 4 vectors. Okay. So now what we can see. So the Dirac equation has the most general solution like this. So I should explain. So these eta and xi can be expanded in a basis. This basis has 2 parts. One is called the spin up part, the other is called spin down part. The spin up part has xi equals to 1, 0. The spin down part has xi equals to 0, 1. Xi are 2 component spinors. Xi S equals to, if S equals to 1, I mean if it is spin up, then xi has two components. Xi equals to 1 0 if the spin is up, xi equals to 0 1 if the spin is down. Similarly for eta equals to 1 0 if the spin is up, eta equals to 0 1 if the spin is down. This all can be okay. So this eta and xi are, so we can form the most general solution. So what I did is I just found a basis, right? So I just found a basis of xi and eta, and I expand xi and eta in the most general form using that basis. Okay. So once we use the basis, so we see that there are two components, 1 and 2, for xi equals to 1 0 and xi equals to 0 1. Similarly for eta equals to 1 0, eta equals to 0 1. So we get two fields, USP for S equals to 1 2, VSP for S equals to 1 2. This has eta, this has xi, again this has eta, this has xi. So these eta and xi are basically the most fundamental of the spinor fields. They are two components spinor. They are the basis vectors of expanding the xi of x in this form. And VSP, CSP, as we saw earlier, that a complex field requires two kinds of operators, B and C, which can create and annihilate particles and antiparticles both. So this is the most general expansion. So, okay, now I have to find the propagator of the Dirac field. So now how do I do that? So let's look at the anti-commutator of psi x and psi y bar. Now what is bar? Now bar is basically the psi dagger field multiplied by the gamma 0 matrix. If you remember the gamma mu matrices, so gamma mu matrices will have, will have 4 components, gamma 0, gamma 1, gamma 2 and gamma 3. So this is psi bar is basically the psi dagger multiplied by the gamma 0 matrix. Okay. Now if we calculate this quantity, we simply get okay. So how much time do I have left?
Yeah, please go ahead. You have, it'll be up to 8:35, so you have time left. It's 8.
Okay. So BPS. Okay. So if I will I will simply conclude, give the results here. So these BPS and BQR dagger, these things. Okay. So these are the anti-commutation relations. Now there is a difference between Dirac fields and scalar fields. The scalar fields satisfy commutation relations. The Dirac fields satisfy anti-commutation relations. Okay, so since they are spinors, since they are fermion particles, they satisfy anti-commutation relations. This is a fundamental difference between scalars and spinors. Spinor particles always satisfy anti-commutation relations to satisfy, because if two particles are replaced, the amplitude is negated, so they satisfy anti-commutation relations. The scalars satisfy commutation relations. So here we will use the anti-commutation relations. This will give a delta function term again. This will again give a delta function term. This term is an outer product of the USP and URQ. This will give nothing but, again, so if we integrate over the delta function terms, we will get S equals to R, right? So this will give a delta RS term and a delta function term. If we integrate over the delta function terms, we will get S equals to R. Similarly here, and we have a summation over S here. Summation is implied because there are two similar indices. Again, we have a summation over these terms. When we do this summation, there is an identity which tells that if USP and USP bar are summed over, we get P slash plus M, where P slash is nothing but gamma mu P mu. the contraction of gamma mu and p mu. Similarly for p slash minus m, right? So we see that if we calculate this quantity, we get this. Now what is the significance of this? Okay, so ISx minus y is simply a quantity which, if we act by the I del slash x plus m operator on the dx minus y minus dy minus x term, where dx minus y is simply the propagator that we introduced earlier, we get back ix x minus y term. So what is the significance? If we again act on sx minus y, s of x minus y, with the I del slash x minus x term, this is derivative with respect to x. So we get 0. So what do we see? This is basically nothing but the operator of the Dirac equation, right? So sx minus y is nothing but the Green's function of the Dirac operator, the Dirac Hamiltonian. And if we substitute this ISx minus y term here, we simply get back the Klein-Gordon equation. So we see two things. Sx minus y is the Green's function of the Dirac operator, and the dx minus y term is the Green's function of the Klein-Gordon operator. So we derive two things from here. So since this is the Green's function and this is the Green's function of the Klein-Gordon operator, we can relate and say that this is the propagator of the Dirac particle from previous analogy, right? Which satisfies this relation p square equal to m square, which is the relativistic equation. Again, we define the Klein-Gordon operator, the Feynman propagator of the Dirac particle as sfx minus y, okay, which is nothing but the time ordered product of psi x and psi y bar fields. And now you see, if we calculate this, so this is actually the propagator. So this has two parts, one for x naught greater than y naught and the other for y naught greater than x naught. Okay, so you see there is a negative sign here, basically because these fields anti-commute. So if we have a field for which x minus y whole square, which is time-like, so if we have two points in space-time which are space-like, so we can always have a Lorentz transformation which always can transform the x minus y whole square x minus y term to y minus x term. So to satisfy this, we have to have something that gives 0 for the Feynman propagator if the points are space-like. So to give that 0 term, this has to be negative. So because the positive quantity and a negative quantity, if both are similar, the term must be 0. That is why this negative term comes. Okay, so finally we have the propagator of the Dirac field, which is simply given by this. Okay, right. So again, we have taken an integral in which we have taken gamma dot p. This gamma dot p is basically and if we take if we apply this operator on sf of x minus y, we will simply get 0. I mean the delta function, right? Why? Because this will give minus ip from here, and this will this is p slash plus m, and if we act this on this, here is the momentum operator. This will simply give p slash minus m. The p slash plus m, p slash minus m will give p square minus m square, and the both terms will cancel, and we will get a delta function. Only this term will remain. This is nothing but delta function, right? Okay. So we have derived the propagator of the Dirac field. So this is the propagator, the Feynman propagator of the Dirac field. Okay. So we define another contraction. This is the time ordered product. This is the non-ordered product. This simple contraction is nothing but the Feynman propagator. Okay. The Feynman rules for fermions. Okay. So now Until
Debapriyo, you have 15 minutes left. Okay,
propagators of the okay, okay, sure. I will
you have 15
tell you.
minutes.
Okay, okay, sure. Thank you. So until now we have derived the Feynman propagators of the scalar field and the Dirac field. Now what we will do is for external particles we will derive the Feynman. We will write down the Feynman rules. The Feynman rule for an incoming fermion is given by this. Okay, so an incoming fermion is given by a U operator, as was previously noted. An outgoing fermion is given by the UR bar operator. Okay, so this is a scalar particle. This an incoming fermion is coming to the vertex, scattering and going away. So one more thing, here time is flowing in the horizontal direction, space is in the vertical direction. Okay, this momentum is the momentum of the fermionic particle. R is the spin, U is the operator of the fermion, U bar is the operator of the outgoing fermion. This is the incoming, this is the outgoing. This is a scalar particle, and these arrows on the Feynman diagrams represent the current. The current is positive for the fermionic particle and negative for the anti-fermionic particle. This is the convention. Okay, so the anti-fermion will have something like this. VRP1, the momentum. This is an incoming anti-fermion. Again, the current is in the opposite direction because it is negatively charged. According to our convention, D bar RP gives the incoming anti-fermion, VRP gives the outgoing anti-fermion. Okay, so this is the condition of Feynman rules. This is for the scalar, the propagator for the scalar, the propagator for the fermion. At a vertex, we always take the minus I lambda factor because of the Dyson expansion. Okay, momentum conservation at each vertex. Okay, and an extra minus sign for statistics. When particles are exchanged, when fermions are exchanged, we always give a minus sign here because of the Fermi principle. So we look at fermions. How much to it? Okay, I will now proceed in a rapid way. So here, a particle with spin s and momentum p is incoming, and here a particle of momentum q and r is incoming. These both are fermionic particles. They interact here through a meson and they go out. The meson is a scalar particle with momentum p prime, s prime, and q prime, s prime, q prime, r prime. We have to calculate the amplitude for this particle. Now, this can be done using two ways, in which the first particle goes to the third particle, and the second in which the first particle goes to the fourth particle. The particles are exchanged, right? So again, so how to calculate the amplitude? The amplitude is calculated so there are two vertices, as you can see. So there is a lambda square factor and a minus I factor. Again, these are the currents. These U bar S prime contracted with P prime, U bar S prime contracted with USP is simply nothing but the contraction at the vertex of the incoming and the outgoing nucleon. These USP and US prime P prime are the currents from the expansion of the fields of the psi and psi bar fields. Okay. So, similarly, U bar R prime, Q prime, U bar Q are this is again a contraction, and this is nothing but the scalar Feynman propagator. P minus P prime is simply the momentum of the scalar, which comes from momentum conservation at the vertex. This minus sign, again, you can simply see this P prime, S prime, again these are contractions. This is again the contraction in the of the propagator, and this is a Feynman propagator. Minus sign comes due to the exchange of particles. Because these are fermionic particles, the minus sign is compulsory in the amplitude. Okay. Similarly for cyber, so again, a nucleon and an antinucleon, they annihilate each other to produce two phi fields. Okay, so this is the condition. So this is the Feynman rule. So how to arrive at this? So we can see that in the internal section of the diagram, now there is not a scalar but a fermion. So we have to replace the scalar propagator by the fermionic propagator. E mu minus P mu prime is simply the momentum of the internal propagator, right? So this is the, as you remember, this is the propagator of the fermionic field. This whole thing. This is contracted with USP, which is the incoming nucleon, and VR bar Q, which is the outgoing nucleon, right? So okay, no, yes, outgoing nucleon is this. So this is the outgoing anti-nucleon. So sorry, I'm the incoming anti-nucleon. So the incoming anti-nucleon is given by V bar. It has spin R and a momentum Q. Okay, and this is the fermionic propagator. The scalar fields, since these are external particles, this will have no contributions. Since these are scalars, if it had been a vector particle, these will have contributions. We'll come to it later. So again, these are two types of diagrams with the particles exchanged, but this time there is a plus because the exchanged particles are bosons, right? These are not fermions, so the exchanged particles are bosons, so this is a plus. Okay. So there is another type of scattering, the nucleon anti-nucleon scattering. The psi bar fields goes to psi bar. This is again by crossing. This is one diagram. This is the other diagram. The amplitudes are as follows. Using the same rules, no change in rules, we'll get the same amplitude. I'm not going into this anymore because this is the same thing again. Okay, so we have concluded the propagators and the amplitudes of the spinors. Now we will come to photons. Now photon is a Maxwell, is the quantization of the Maxwell. The Maxwell's equations are 4 equations in vacuum. These are given in heavy side Lorentz units. This is the standard units in high energy physics of vector mu, which is the vector, the 4 potential of the E and B fields. We can write these equations in a compact form like this, right? Where E is given by this, B is given by this, mu is simply this, and J mu is rho and G. If we introduce the field strength tensor, then this again comes into a very small form with current conservation, right? Now, these are all fundamentals of electrodynamics, which I think is done already in your courses. What is important is that the fields E and B are unchanged under a gauge transformation. Okay, so this is a gauge transformation. Chi is simply a function of x. Okay, so this is a gauge transformation, and simply the fields are unchanged under a gauge transformation. Okay, so if we choose chi in such a way such that del square chi is equals to the gradient of the, such that this equation, this is the Lorentz gauge condition. So we get a very simple equation. This equation is reduced to a very simple equation like this. Okay, now this equation is the most fundamental equation that is used in quantum electrodynamics of photons, or to quantize photons. Okay, so J mu is the current, A mu is the 4 potential, del mu mu equal to 0 is the Lorentz gauge condition. Now we can introduce another gauge transformation such that del square lambda equals to 0, such that this equation is still valid, right? Such that this equation is still valid. We introduce a gauge transformation lambda and we apply that. Okay, so so if 0, then mu satisfies this equation, right? So if it satisfies this equation, we have a general solution. We have a solution like this. Again, a free particle solution with epsilon mu q, where q is the momentum of the particle of the field, not the particle. I will come to particles later. Mu is simply the Lorentz index of this field mu. This is a plane wave solution because it satisfies this equation, the Lorentz equation. Okay. Next.
Debapriyo, you have 5 minutes left. Okay.
Okay. Okay. Let's see how much we can proceed. Okay. So I think I will. Okay. So this is a Lorentz condition. This, once we put these ansatz into this equation, we get this condition. Now we choose lambda in such a way, that lambda parameter we choose in such a way such that this epsilon mu epsilon, the zeroth component of epsilon 0 goes to 0. That is, the time component of epsilon mu goes to 0. We choose lambda in such a way such that the time component of epsilon mu goes to 0. If it is 0, then we get a much more simpler condition, epsilon dot q equal to 0. Right, because epsilon mu q mu equal to 0 was always there. Now epsilon 0 equals to 0. So epsilon dot q becomes equal to 0. Once this is 0, we see that epsilon is perpendicular to the q vector, the momentum of the field. So if we choose the momentum of the field in the z direction or the z direction, then we can choose epsilon in two ways. One in the x direction, the other in the y direction. Right. There are other two ways in which we can take a linear combination of these two epsilon 1 and epsilon 2 to form epsilon or epsilon L, which are called the right circular polarizations and the left circular polarizations. And using these polarization fields, we can expand mu in a much more general way like this. Again, epsilon mu I, epsilon mu p are the epsilon mu I p, epsilon mu I star p are simply nothing but the polarization vectors. And API dagger are simply the creation and annihilation operators of the photons. Now, okay, so now we have raised the this mu x to the status of an operator. Okay, so we have introduced an API and API dagger factors, and we have introduced the polarization factors also. This is the most general expansion of the photon field. Okay, next. Okay, so this I have discussed already. Okay, the photon propagator. Okay, so the photon field, similar to the scalar field and Dirac field, if we have the photon field and if we take the time-ordered product, we get simply something like this, where pi mu nu is the kernel. We have to find out this kernel, what this kernel is. Similar to there is a IPX minus y term. So we have to find out the kernel. How to find out the kernel? Okay, so we see from the equation of the field tensor that the Maxwell's equations can be written like this. And if we have the Maxwell's equations like this, then in the momentum space, this equation becomes like this. And if we try to invert this equation, it is impossible because the determinant of the operator is 0. Now, so what to do? So we take a Lagrangian. Okay, so we take a Lagrangian on this form, and if we vary. Okay, so this is nothing but the Lagrangian of the photon field. If we take the Euler-Lagrange equations, we can simply get back the Maxwell's equations. But here xi is nothing but Lagrange multiplier, del mu equal to 0. So we impose the del mu equal to 0, mu equal to 0 constant via Lagrange multiplier. Okay, so if we vary this equation, we get the Maxwell's equation. Now with the xi terms, the equations of motion are with the xi term included, right? So with the xi term included, the Maxwell's equation something in the momentum space becomes something like this. Okay. Okay. So what do I claim? I claim that this, if I use this pi mu, if I use this as the propagator, I simply get, what do I get? I simply get the Green's function of this propagator in the momentum space. So since this is the Green's function in the momentum space, this is nothing but the inverse of this operator. Okay, so if I use this Green's function, so I get the inverse of the operator using the Xi field. The Xi field was not present, then it was not possible because this operator would have been singular, so it would not have been possible to invert the operator. Using the Xi field, we invert the operator, and after we invert the operator, we get something like this. Again, the epsilon prescription has been used, as you can see here. So this is the propagator of the photon, right? So we have two gauges, three gauges actually. What we mostly use is the Feynman tubed gauge, where Xi equals to 1. If we use Xi equals to 1, the propagator simply reduces to this. The other two gauges are not so important for QED. Okay, so I have almost reached the conclusion. Give me 5 more minutes, I will conclude now. So until now, we have seen the propagators of the scalar field, the Dirac field, and the photon field. So what I will do now is I will couple all three fields into one and see some physical processes in which actual QED is taking place with actual particles which are real world particles. So first we see an electron scattering. So in electron scattering, we see two electrons scattering off each other, exchanging a photon and giving us 2 electrons more, right? So this is an electron-electron scattering. Okay, so again there are two Feynman diagrams. Now as you might see, there is a gamma mu factor here. So this gamma mu factor is nothing but the contraction of the vertices which comes when there is a photon is interacting with a fermion, right? When there is a photon interacting with a fermion, this gamma mu factor comes. Again, there is a square term. This minus I comes due to eta mu term. Eta mu term comes from minus I, and the g mu are contracted with the gamma mu matrices, and they give a minus I for each vertex. And if we replace the vertex, there is a minus sign. Again, there is an incoming particle with spin s and p, and there is an incoming particle q and r. Again, they are contracted in this way. This is the photon propagator, E prime minus p of the momentum of the photon, due to the momentum conservation of the vertex. So this is the electron scattering and the amplitude. So this is the amplitude. Okay. So we are taking the propagator of the electron field, the Dirac field, the photon field, and we have created the amplitude of the electron scattering. Next, electron positron scattering. So here an electron and a positron come, they exchange a photon and they go out. Again, there are two types of diagrams. The one in which the electron positron comes, they annihilate into a photon, again they go out. The other in which they exchange a photon, don't annihilate themselves. Again, there is a minus sign because there is exchange of particles. Right, so these Feynman diagrams are two different diagrams with exchange of particles. Again, similar amplitudes. This time there is a crossing of the particles. I will explain if you want me to, but there is no time since, so I will skip. So I will. This is very similar to the previous process. Just we have to take the diagrams of the propagators and apply momentum conservation, and we get this amplitude. Electron positron annihilation. Okay, so in this process, two electron positron come and they annihilate into 2 photons. As you can see, this is a process in which here there is an electron propagator. There is an electron propagator also here. So we will use those propagators here. Again, now the most important part in this diagram is that there are 2 outgoing photons, as you can see. So for 2 outgoing photons, there will be a polarization factor. So as the external particles. So that was the polarization, right? In case of photons, that was the polarization. So here the polarization has come. This is the polarization of the particle. This is the polarization of the second particle, the second photon. This is the first photon, the second photon of momentum p and q. This is the propagator of the Dirac field, the Dirac fermion, which is here. These propagators, these are again the incoming states. The currents are given by these arrows on the Feynman diagrams. Momentum are given by these arrows alongside the Feynman diagrams. Okay.
Debapriyo, I'll have to ask you to wrap up quickly. Thanks.
Yeah, I have almost finished. Almost finished. This is the last slide actually. So this is the electron positive ionization. So this is the amplitude. And next we come to Compton scattering. This is the last slide. In Compton scattering, again, there is an incoming electron which scatters of a photon, and again a photon leaves and the electron leaves. Now this can be done in two ways. The scattered photon may come out first and the incoming photon may be scattered later, or the scattered photon may come out later and the incoming photon may come out may scatter first. So there are two exchange of two photons, but the two bosons. So there is a plus sign. Again, there are two outgoing photons. So this is epsilon in and out. So there is an incoming photon and there is an outgoing photon, but their photons are neutral particles. So there is no difference. Their fields are real. Okay, and this is the propagator of the, again, this is the electron propagator for the first process. This is the electron propagator for the second process. There is a outgoing electron here. There is an incoming electron here, and there is a coupling term because there are two vertices. So I think this concludes all of the scattering processes, the physical processes. If you have questions, you can ask me now. Thank you.
Okay, thanks a lot, Debapriyo. So I just had a very naive question.
Yeah.
Okay, so as far as I know, that the processes that you were describing using, let's say, electron scattering to electron positron, or electron positron scattering into themselves. So these are all connected by something called crossing symmetry. Am I correct?
Yes.
So just out of curiosity, so do you know that is there an underlying symmetry, or is there an underlying deeper reason for this to happen? I mean, because this is a very, very general statement in quantum field theory.
Yeah, crossing symmetry is one of so what I do, so my current research is in this field actually. So what I do is I take crossing symmetry, I take analyticity of the S matrix, and I take the unitarity of the S matrix, and without using Feynman diagrams, I try to constrain the coupling terms of various interaction processes. So crossing symmetries, as far as I know, is the one of the most fundamentals of quantum field theories. Exchange of particles and antiparticles on both sides of the reactions is something very fundamental. I don't know if there is more a more fundamental reason behind this, but as far as I know, crossing symmetry is the most fundamental of I mean, exchange of particles and antiparticles. Since you see, we are always dealing with complex fields, right? So complex fields will always have particles and antiparticles. Now, in a reaction, in a particle reaction, these antiparticles and particles can always be exchanged among themselves without affecting charge conservation or without affecting momentum conservation. Since this can be done, I think charge conservation and momentum conservation if this can be preserved, I think crossing symmetry becomes the most fundamental thing.
Okay, thank you, Debapriyo. So are there any questions? I'm sorry. Are there any questions from the audience?
So as you said,
okay, so
crossing symmetry actually comes from the complex nature of the fields and the momentum conservation and the charge conservation. So I think there is nothing more fundamental to momentum conservation and charge conservation in any of physics.
Right. Okay. So I don't see any more questions in chat. So I'll just conclude by asking one more question. Okay.
Okay.
So related to this, so so the fields that we were discussing so far are all Dirac fields, right?
So I have discussed scalar fields, Dirac fields, and the photon field.
Exactly. So they're all Dirac particles.
No, scalar particles are not the Dirac particles. Dirac particles
not scalars, but fermions are Dirac particles, right?
Yeah.
Okay. So I was asking that, do you know any extension to Majorana fermions? I mean, do these kind of things also hold for Majorana fermions?
Okay, so Majorana fermions are I think I forgot what
Why
Bangalore
I
formulas are.
asked this
Can
question?
you?
Right. So there's a common notion that neutrino, as you know, a
Yeah,
common mass model for neutrino, as you know, that the standard model does not give any mass to neutrino, but it has a mass. So a mechanism
yeah,
for it is that by considering it to be a Majorana fermion,
right.
right?
Okay,
And you have to consider all kind of cross-section processes of neutrinos, because experimentally you have to test the numbers, a few numbers.
okay.
So that's why I asked this question, since you work in this area of scattering and all that.
Yeah,
So
yeah.
do you have any idea of Majorana fermions and the extension to it?
Majorana fermions, I think are they neutral fermions? I can't remember actually. What are the
Yes,
basic?
yes.
What is the fundamental property of Majorana fermion?
That is, under
Do
a
you know?
CPT transformation, it goes to itself. The field goes to itself. That means it's its own
I see, I
identifier.
see, I see, I see, I see. Okay, so there is okay. So okay, right. So it must be a neutral party, right? Because if it is going to see under CP2 itself, so
Absolutely.
yeah, it has to be neutral. So this is something that I compute.
Okay, okay. Thanks a
Yeah.
lot. So I think